Hello and welcome to Calculus tutorial. Today in class we were taking a look at derivatives and motion, so I just want to do a quick recap of that and summary for you. There are two main subpoints off of that, instantaneous velocity and average velocity. We spend most our time with instantaneous velocity because instantaneous means 1 point, the slope at 1 point, which is the definition of the derivative. So we do most of our work here, but we can't ignore average velocity, especially because if you're taking physics, that is most often what you calculate, because in physics you don't do any calculus, at least not at the high school level. So first, derivatives and motion. How are those two related? So to start that off, I'm going to put my two graphs here. You'll see that I start many things this way. We'll call that one f as usual, and then if we take the derivative of f, we get f prime. And so what we learned today is that if this one is position, then this one must be velocity. When you take the derivative of position, you get velocity. Now, why do you get velocity? Well, to explain that, think if you're in physics, what is the definition of velocity? It is the change in position over the change in time. You probably don't call it average velocity, but never mind. We'll talk about average velocity later. But I'm hoping this looks familiar. You saw something very similar to this in Algebra 1 a long time ago. Change in position over change in time hopefully looks a lot like delta y over delta x. Same idea, because this is our y value here and this is our x value there. And so that is simply the definition of slope. So when you take the slope of position, also known as the derivative, you get velocity. So if you have your function for position and you want the velocity function, all you have to do is take your position function and take its derivative. And you'll have a function to model velocity. Alright. So now that we have an idea of the relationship between derivatives and motion, we can now start talking about instantaneous velocity, which will be the slope at 1 point, which is the definition of the derivative. So here we have one quick example. Suppose you throw a rock upwards off a 30-meter cliff. You throw the rock at a velocity of 5 meters per second straight up. And the equation that models that, the height, which is the position, is given below. So you have that equation there, and we will talk more about where all these numbers come from and why they go where they do. But for now, we don't need that. What is the velocity of the rock after 2 seconds? So I want velocity. So velocity, just like we just wrote on the previous one, is the position's derivative. So what is that? Well, to take the derivative, use the power rule. 2 multiplies down to the negative 4.9. You get negative 9.8 t, which hopefully that negative 9.8 looks familiar to you if you're in physics, plus 5t. The derivative of 5t is just 5. And then the derivative of 30 is 0, so we don't need it. And so now we have an equation that models the velocity of this rock that we threw. Negative 9.8 t plus 5. And we want the velocity of the rock after 2 seconds. So we have to plug in 2. So we have negative 9.8 times 2 plus 5, which equals 9.8 times 2 is negative 19.6 plus 5 gives us negative 14.6. And that is our velocity, so that is meters per second. So after 2 seconds, the rock is going down at 14.6 meters per second. Another way to put it is we just found the slope of that point right there. So that slope right there is negative 14.6. So instantaneous velocity is the slope at 1 point. What about average velocity then? What will average velocity do? Well, this one doesn't take any calculus, which is why you work on it in physics class in high school. It is going to be the slope between 2 points. As you can see, it's still a slope, but it's between 2 points because you are not finding the instantaneous slope, the slope at 1 point. So hopefully the first example makes complete sense. You take a road trip to LA. After 1.5 hours, you reach Bakersfield, which is 100 miles away. Then 2.5 hours after that, you reach your destination after traveling another 250 miles. So first, what was your average velocity on your way to Bakersfield? Well, remember, velocity is simply the change in position over the change in time. So for Bakersfield, that will be 100 miles divided by 1.5. Now that's hopefully pretty intuitive. You have your distance divided by your time, and that will give you velocity. Just to make sure I don't get this wrong. 66.666. So 66.6 miles per hour. Oops. Sorry about that. So 66.6 miles per hour. Now that may not look like the slope between 2 points, but we actually did do the slope between 2 points. The first point was just so easy that we didn't think about it. When we started this trip, 0 time had passed by, and we had traveled 0 miles. That's when we started. But then we traveled all the way to an hour and a half later and 100 miles. And so if you take the slope between those 2 points, subtract the y's, subtract the x's, and of course you can see how we will get the exact same thing. Now for the next one, we are definitely going to have to start with the slope between 2 points because we aren't starting at 0, 0. So 2.5 hours later, we reach our destination. So we're going to start here at Bakersfield, 1.5, 100. 2.5 hours after that, we have been traveling for 4 hours. 1.5 plus 2.5. And you reach your destination after traveling another 250 miles. So if we traveled another 250 miles, we have now traveled a total of 350. Okay. Hopefully you can see that we are going to do 250 divided by 2.5, but I want to make sure you can see how you can get that from 2 different points. All right, this is Bakersfield, and this is how long we've been traveling once we get to our destination. So to find the slope between 2 points, we do 350 minus 100 divided by 4 minus 1.5. 350 minus 100 is 250, and then 4 minus 1.5 is 2.5. And so 250 divided by 2.5, that is 100, isn't it? 250 divided by 2.5, yeah. Doing mental math on the fly is always dangerous. All right, so that is 100. We were definitely speeding at some point. Now this is average velocity, so does that mean we were always going 100 miles an hour? Probably not. Sometimes we were stopped, sometimes we were going faster, but on average, we were going 100 miles an hour. All right, I'm hoping that makes complete sense for a simple motion problem like that. But what if we do one where we just have the equation, like our rock example? What is the average velocity of the rock over the first 2 seconds? Well, we are going to take the slope from this point and this point here. And so the average velocity will be the slope of this line here. Wish I could draw a better line. Sorry about that. Are we always going to go that speed? No, the rock does not follow this path. It goes up and back down. But on average, that will be the velocity. And so our first point is 0.30. And our second point is 2,20.4. I had to go double check that number. You can see it's almost 20, but it is actually a little bit above 20. If you want to check that, just plug 2 into the equation. And so if we want to find the average velocity, we simply find the slope between those 2 points. 20.4 minus 30 over 2 minus 0. So the bottom is easy. 20 minus 30 is negative 10.4. Divide that by, I can hopefully do that one, negative 5.2. We were in meters per second on that one, I believe. Negative 5.2 meters per second is the average velocity. So if you were somehow able to get a rock that simply went at a constant negative 5.2 meters per second from here to here, it would meet up with the rock you threw up and then came down because of gravity at 2 seconds. So that is the slope between 2 points, whereas instantaneous velocity, which we will be working at more, is simply the slope at 1 point. So hopefully that helps clear a few things up. See you next time.